Okay, let's make a start. So, welcome everyone to November's A3D3 seminar. It's been a few months since we last had one of these, but we've got a schedule for the next few months again. So we're hoping to get back into the swing. So today, I'm very pleased to introduce our speaker, who's Dr. Miles Cranmer. He's an assistant professor in data intensive science at DMTP and IOA in Cambridge. I first met Miles about 6 years ago when he was an undergraduate at McGill, senior undergrad, and was looking for graduate school positions. And we had some very interesting discussions at Caltech. And I think we even offered him a position, but he decided instead to go to Princeton. But that's the way it goes with the really good students. So after his time at Princeton, he did a brief internship at the Simons Foundation in New York. And since I think just over a month ago, 2 months ago, he's now new faculty in Cambridge in their large growing data intensive science group. So Miles will be talking to us today about foundation models in AI and introducing, I hope, Polymathic AI. So Miles.
Yeah, thanks so much. Thanks for the introduction. Thanks for having me. So today I'm going to present a new research collaboration that has some new papers out. So this is a collaboration kind of out of the Simons Foundation, but with collaborations at a few different institutions. And the point of the collaboration is to make a foundation model for science. So I'm gonna talk through what this is. So in the past maybe 2 years, you might have noticed there's been this huge shift in how we do machine learning, especially in industry. So for example, natural language processing in industry, it used to be that you would have some specific language model, you would train it on your data set to do some task, and you would just take that model as your kind of final version. Now what people do is they take a very large model, train it on basically the entire internet, like all of the text you can get, and then you do what's called fine tuning, and you kind of take this general pre-trained model and you kind of fine tune it for a specific task. So for example, like ChatGPT is an example. It is this like GPT-4 pre-trained on the entire internet and then tuned to be like a friendly chatting bot. Similarly, GitHub Copilot, same thing, but for code. And there's open source versions as well. You see the same thing in vision. So I think the most obvious example is Stable Diffusion, these generative art models. Those are just trained on massive amounts of image data. And then you can fine tune them to do specific tasks like in painting or like a specific art style. So they're pre-trained on general data and then fine-tuned on a specific task. So it's kind of a completely like different way of kind of doing machine learning in general. So rather than I have a data set, I have a model, I train the model on my data set. Now you have kind of this massive general data set and a specific data set for your problem. So it's a shift in the way we use machine learning, but it's really starting to dominate many different fields. Like language and vision, you would be crazy to not take a pre-trained language model, right? Like it's just becoming standard in these fields. So the way a foundation model works, you have this large, very general model, like a universal model for prediction tasks, maybe generating data. You train it on just massive amounts of data. Maybe you train it on text data. Maybe you train it on multimodal, so like multiple types of data, like text, images, speech. And you traditionally train this in a self-supervised way. So maybe it has some text and it tries to predict the next word. There's masked language models, which you basically randomly mask out parts of a sentence and you try to predict from both sides. Once you have this model, you can fine tune it for specific tasks. So if I have like question answering data, I can kind of keep training my model, but on this very specific data set that I've curated. Or maybe you have some like reinforcement learning with human feedback model. So it's like a reward model that predicts like, this is a good answer, this is a bad answer, and I kind of train my model on that. Or, I mean, there's many other tasks. So it's kind of a new way of doing machine learning, and it seems really powerful. So the key idea, take a general model, can intake variety of data. You train this general model on as many examples as you can fit onto your computer, typically self-supervised learning, and then you take the model and you fine-tune it for specific downstream tasks. I mean, often you don't even need to fine-tune it. You just like use it out of the box. So as an example, language, so autoregressive language models, you give a sequence of vectors representing words, which are tokens, and you get this language model to predict a vector of probabilities over the next word, and it gets rewarded if it predicts the probability of the correct word, right? You optimize this on the entire internet, pretty much. Just all the text data you can get. And I guess I'm going to skip through these. So the same is true for images. So for image data, you typically have like diffusion model. So it generates images from noise. You would train this on many different, perhaps art styles. So train it on photographs, diagrams, paintings, whatever. Once you have that model, you could, for example, like use the model as is, or maybe you have like a specific task. You want it to draw images in like, I think it's like Studio Ghibli style. I think it's like, yeah, you just generate like specific images. I think that's Bill Nye in Studio Ghibli style. And then you would generate like that specific art style. Now, the nice part about this is it's already learned the concepts of like what a face is and what facial structure is from its massive catalog of data, right? So when you show it images for the fine-tuning step, it doesn't need to learn these concepts of like what is a face, where are the eyes positions. It doesn't need to learn that from scratch. It just kind of specializes its already learned concepts. And that's really the nice part about foundation models. So you could do fine-tuning, but you could also use embeddings for different tasks. So maybe like you do a k nearest neighbor search in the kind of like vector representation space, and you find like this close image. And you see here, like if you just did a direct pixel to pixel comparison, you wouldn't find it, but in this embedding space, maybe it nicely matches up. So like this helps because I think by training on an extremely large data set, you learn very general patterns. So vision models learn like facial structure, what a typical like physical scene looks like before it's taught to draw a specific way. Language models may learn what the grammar of language is before translating, right? So if you just train a model to do language translation, it has to kind of bootstrap all of these different concepts. It has to learn all the grammar of, say, like English and French, and then translate. Whereas a pre-trained model maybe already knows grammar, and so it only has to learn the mapping between the languages. So I think like, so I'll just say, I think why this actually helps is it's really because it comes down to priors over function space. So machine learning researchers, including my whole PhD, have historically worked really hard to come up with like smart biases in networks. Like, okay, I want this network to conserve energy. So I worked on like this Lagrangian neural network. And then, so if I design my network in that way, it's going to be biased towards that class of function. So for example, like convolutional neural networks have translational symmetry is another example. Foundation models is kind of like, let's throw out our good ideas that I spent my whole PhD on, and let's just learn the inductive bias or the prior. Let's learn the prior over functions from data. Let's just make a very general model, throw tons of data at it, and it's going to kind of pick up these concepts in kind of like a more natural way that suits the network. So I think it's interesting if you note that the state-of-the-art vision models are vision transformers, even though they don't really have like translational symmetry, which is kind of like what everybody said. Okay, CNNs are good because they have translational symmetry, but it turns out like if you just take a model without that symmetry, but it's very flexible and you just give it enough data, it kind of learns the same inductive bias, but it's like by not imposing that prior in like a very strict way, you're kind of like smoothing the optimization landscape. That's kind of how I think it works. It's like because you're letting the network design how it wants to incorporate that prior, it basically learns better. Like so, during my PhD, I worked on this thing called a Lagrangian neural network. So it's basically like you force the network to conserve energy in a physical system. It's really hard to train these things. Whereas if you had just shown it many examples of energy conserving systems, maybe it would kind of like pick up this concept in a more, I don't know, we'd kind of like learn it smoother than having to go through this crazy like gradient scheme. That's kind of why I think this works. So, okay, the pitch of polymathic AI. Can we do this for science? So we know that vision and language are dominated by this approach. You take a pre-trained model, you fine-tune it for a task. Can we do the same thing for science? Can we take a general model that is pre-trained on tons of data sets in science, take that model and fine-tune it to a specific scientific task? So like, I think one thing that we implicitly and falsely assume is that a randomly initialized network is an uninformed kind of neutral prior. But no, a randomly initialized neural network is actually like a very, I guess, opinionated prior over the space of models. And it's a very bad prior because if you have a pre-trained model, you can pretty much like always get better performance when you're fine-tuning compared to just like a randomly initialized neural network. Like I think it's always better to just pre-train a model on large amount of data and fine-tune it rather than train a model from scratch on like a medium-sized data set. It's just like a randomly initializing a neural network is just not a good prior. That's what I view as kind of one of the takeaways here. So, okay, why would this work in science? Actually, I'm going to skip this slide. Why would this work in science? So, in many different scientific kind of problems, there are shared concepts. So, for example, let's look at the reaction diffusion equation, which is like chemistry, and shallow water equations. They're completely different PDEs, right? Like these PDEs look nothing alike. But if you study their behavior, they both have waves. They both have these kind of constant velocity wave-like behavior. So in science, there's this interesting thing where you can have completely different domains, and there's some shared concepts between them. And so the conjecture of this collaboration is like, okay, maybe if you pre-train a model on vast amounts of scientific data, it might pick up like a general grammar for science. And then when you fine tune it, maybe it won't have to learn the concept of a wave from scratch. It will already know what a wave is so that when it is fine-tuned. It just has to learn like the smaller changes to the function. So that's the pitch. And you could kind of look at maybe like all of science, zoom out. So you could think about, this is kind of abusing this term a bit, but you could think of this as like universality classes. So if I think about all of science as kind of like groups of shared concepts, you could think of like, okay, causality, measurement, modeling, those are like, maybe like all of science has those. Maybe I zoom in on part of it, like statistical analysis. Okay, maybe like specific problems are in there, like cancer risk metagenomics. Maybe over here is like dynamical systems. Within that, there's many systems that have conservation laws, right? That's like a shared concept. And so maybe like if I train on problems here, maybe I could like generalize better over here, or maybe like I train here and I can generalize all the way across because there's these very abstract shared concepts. And it's kind of like if you learn 3 languages, it's easier to learn a 4th language than it is if you only know 1 language. It's much harder to learn the 2nd language. It's kind of a similar idea here that it's like you have all this strong understanding that you can kind of quickly apply and learn things quicker. So this is kind of our conjecture. Like there are a lot of shared concepts in science. So maybe this idea of foundation models will work for science too. So this is Polymathic AI. So it's a new research collaboration. It's about like 25 people right now. So it's trying to build these foundation models for science. So we have like pure machine learning people. We have a lot of pure scientists and kind of people in the middle like me. It's housed primarily at the Simons Foundation, but also Cambridge, NYU, and elsewhere. And essentially what we're trying to do, like the biggest point that you would kind of struggle if you tried to make one of these yourselves is that you need massive amounts of compute. Like to train a foundation model, it requires like, hundreds, if not 1,000 GPUs for running for like a long time. Like it is a ridiculous amount of GPUs. So we're essentially trying to allocate resources so that we're trying to allocate resources and data sets and kind of machine learning expertise, the models, so that we can actually like build this thing. So like we're actually trying to build a foundation model for science that you as a scientist kind of using machine learning could kind of take our model and fine tune it to your task, and you might get better performance than kind of training from scratch. That's the pitch here. So the current stage is still research and development. Like if you look at the time between like the original transformer paper in 2017 and ChatGPT, it's like 5 years. So I think we can be a bit faster, but I think like to the point where we release a general foundation model, it's probably like 2 to 5 years out. So we're still kind of in the heavy research and development stage, and I'll show you a couple of our recent papers. So I guess in terms of research directions, one thing we thought about at the beginning is like, okay, there's 2 ways of going about building a foundation model for science. Like we know that language models, just these like very general massive transformer models, if you scale them up, you get better and better performance on language, right? So this is kind of like these curves here are kind of like contours of improved performance. And so as we go up, we get better and better performance. We also know that like in science, we're kind of at this tiny scale stage. Like we have these very specialized models like UNet, GNNs, like LSTMs, like for kind of different tasks. Like you train a UNet to do like physical emulation of a simulation, whatever. So it's kind of like these small models you train on a specific task and they do well. We don't really know which way we should go. There's kind of like, there's two directions here. So like one is, okay, maybe we could take like this kind of language model and just like give it different data. So like maybe that would work. And maybe the transformer is kind of the secret sauce. And it's like, that is what makes these models scale so well. But like maybe also it's just that no one's tried like throwing hundreds of GPUs and like massive amounts of data at a traditional model that was used for science. Like we don't know really which direction to go here because they're both unexplored. So I'll talk. So the way we're kind of working is we're approaching both directions. We're trying both because we don't know, and we're going to try to see like, okay, which one actually gives us the performance. And I think once we know that, then we can kind of like scale up and really train one of these. So the first direction, okay, what if we took a language model and trained it to do science? So this is a direction. We're basically trying to take a language model and specialize it to scientific tasks. Again, this is pre-training. We're not fine-tuning. We're pre-training a model. So one thing you'll notice that if you use ChatGPT, if you ask it to multiply two like random 4-digit numbers, it pretty much always fails. So like if I say what's this times this, it tends to kind of miss the middle numbers. Like the first numbers it can kind of get from statistical inference, and the last numbers similar, but the middle numbers it always kind of messes up. It's just like guessing. So it seems like ChatGPT doesn't have a good understanding of what a number actually is and how they kind of like numbers are not, they're not text. They have specific continuous meaning, right? They have these like special properties. So like if you look at how language models read numbers, there's kind of different ways of approaching it. So like one is maybe you just like break it into characters. So like 1.23 would be 1.23, right? So there's some more sophisticated methods. So like P10 is one example. It kind of takes this number and splits it into these tokens. So it's like a negative is one token, a 6 is another token, then the characters, and then like an exponential character for the number of digits. P1000 is kind of like, okay, I'm going to combine the 3 digits of precision. So like negative 6.02 becomes negative 602 is a single token. And then I have another like exponential token. And you can see here, this is the vocabulary size. So if we want to have a token for every single number, it blows up the vocabulary. So we have to learn a lot of different tokens to deal with this. As we go down to like FP15, so this is essentially, it's basically like every single number has a different token. And so it's this low precision representation, but basically every single number with 3 digits of precision has a single token assigned to it. And you can see the vocabulary size here is very large. But the problem with all of these encoding schemes is none of them are continuous. They're all discrete, which is fine if you're dealing with words, but numbers have like very specific properties. You should want, like if I gradually change my input to a transformer, the output should also gradually change. But right now we don't have that. If you change like a single decimal point in a language model, the output will just completely differ, right? Because you just have like different tokens. So we came up with this idea. So it's led by Siavash Golkar, and it's called XVAL. So it's a new type of encoding for numbers. it's basically you have a specific dedicated token for numerical values. Just call it num. So you have like the special word num. You have your original sequence, but then you also have another sequence, which is the numerical values. So like 5, if my number is 5, 7.4, if my number is 7.4. Then when I'm computing the embeddings, I basically take that numerical value and multiply the embedding. I'm basically scaling the embeddings by the size of the number. So it's nice because I only need like a single token for a number, and I only I have like a completely continuous representation. So the way decoding works is I predict my special number token. So like I have my token head, okay, it predicts like, okay, here's a number. Then I have a separate head, which is like dedicated to predicting numerical values. And if I choose a number token, it's going to flip that switch and I get the number out. So you see like, if I change the 7.4 by like an infinitesimal increase, the output will change the exact same infinitesimal. Like it's a continuous encoding, which is like really how we should be doing it if we're actually trying to compute, like scientific calculations with a language model. By the way, I'm happy to take questions throughout the talk if anybody has one. You can just speak up if you do. Okay. I will continue.
Can I ask a question here? Is this the idea that, okay, the model will predict this word noun, and do you need a regression, like another model to do the regression task?
Yeah. Yeah, so it's one head. So it's not a separate model. It's the same transformer, but it's like one head predicts the tokens, and then another head. It's like a separate MLP at the last layer is kind of predicting the numbers.
Oh, I see. And there was automatic skip the tokens, which is not none.
Yeah, exactly. Yeah.
Oh, okay, that's cool.
Yeah. So yeah, good question. So like one thing people will ask us is okay, what if you have like massive dynamic ranges? So the thing I didn't mention is we actually normalize these in going in. So it's this kind of like we basically put it through a tanh. So it doesn't really like ever blow up. Now, the problem with like mapping these through a tanh is if you have like 10 to the 100, it's not really going to know it's 10 to the 100. So for those cases, like if you know that number is going to be in your data set, you might kind of like do both things. So like maybe give it the numerical value, but then also give it like the token, like the normal tokenization. But like if you know the kind of distribution of the numbers in your data set, as we often do, if we have like, like if we know our scientific data set, then you could probably use this. And so you could also take a language model, keep most of the tokens, and maybe just like add another token just for dealing with numbers. So you could use this in fine tuning too. I mean, it would change things obviously, but then you wouldn't be starting from scratch, I guess.
A follow-up question. I think, okay, I understand this method, but did you check the scalability of this model? Because, regression tasks is much harder to train compared to multi-class classification task, right? That's essentially the what transformer try to do to predict what are the next word in your vocabulary. I mean, normally it's the regression task. It's very hard to train to a high precision.
Yeah. Oh yeah, totally. Yeah, I completely agree. Yeah. So one thing I didn't mention is like the loss function. So obviously you can't do like perplexity on these and then have this be like also perplexity. So what you do is for the numbers you do mean squared error, and the words you do so you do a combination of mean squared error and then also classification loss on the number token. and then mean squared error on these. Of course, like if your scales are weird, then you're kind of like screwed a bit, but you would generally like want to kind of normalize the data before it goes in. But I think there's still obviously some research directions here. But it is like a fully continuous mapping from the input to the output, which is really what you want for doing scientific data analysis. So if you actually use this, if you take a large language model, you train it on some like kind of scientific language task, like maybe you're describing a physical thing. Normal language models with the normal tokenization scheme, you get these kind of artifacts whenever you jump between tokens. So you can kind of see those there. But the orange one is with xval, so it is continuous, right? So you don't get that anymore. So we did this on this climate data set. We basically give it to the language model as a JSON file. So it's text, but it has like numbers in it. You basically stick this in, you try to predict the next temperature. And what you find is it does much better. So the loss is improved. I mean, like keeping in mind, this is a specific task that is suitable for this tokenization, but it's kind of like, I think it helps stress that like, if you want to do this type of task, you really need this type of encoding. So it's both like more accurate, faster, because you have less tokens. You only have one token per number. Yeah, so it does give you like a faster result because you have less tokens. So you kind of see like the different encoding schemes, you get these weird artifacts whenever you're kind of like switching between 10 to the negative 1 and 10 to the negative 2, you get these weird tokens. So I think like at when you reach like 1.0 in a language model, it kind of like does something a bit weird. But you see with xval, it's continuous, so you don't really get that. Okay, so that was the first one, the first paper we put out. So that's xval. And that's kind of like, okay, what if we want to take language models, put them on a scientific task? So we're continuing that research direction. Obviously, there's a lot more development. The other direction is, okay, what if we just take one of these like traditional science models and just make it big? We just scale it up. So this paper is called Multiple Physics Pre-Training for Physical Circuit Models. So a common task in the more simulation-heavy sciences. So you have like this really expensive simulation and you want it to be fast. Maybe you want to do like inference with it, or I don't know, like some kind of fast modeling. So you want to find like a approximation of that simulator that you can just do really quick inference on. So this is basically the task. You're trying to predict the dynamics for maybe this fluid flow. So this is like the velocity of the fluid, the density, the pressure. And you're essentially trying to predict the next step in each of these frames. So multiple physics pre-training, basically pre-training on multiple physics. It requires a couple different ideas to actually make it work. But it's kind of like you pre-train on a variety of different physics simulations. I mean, it doesn't have to be simulations, but we did simulations. So different physical PDEs. After pre-training, you fine-tune on a new PDE that you didn't see in your training set, and you evaluate it. So this is the paper. So the takeaway is that if you do multiple physics pre-training, you can basically always match or outperform kind of task-specific baselines. So if you have like a baseline model trained just on this PDE, it's always going to do worse than if you had shown that model many kind of unrelated physics examples. Like the really interesting thing, they don't even need to be that related. So one example we did is we took our model and we basically trained it on cat videos, and it still outperformed random initialization. Like random initialization just is not good. Like it's a bad prior. So if you train it on anything kind of remotely physical looking, it always kind of improves it. And the closer your, I guess, simulations kind of get, the better the fine-tuning performance. But even if they're completely unrelated, you'll still get better performance. So the takeaway is like you should always take a pre-trained model. Like pre-training is really good. So how do you actually do this for if you have like completely different physics? So that's what this paper is about. It's specifically for solving 2D partial differential equations. So for example, like say we have this 4-field PDE. We have velocity, pressure, density at a given space and time, right? And we want to embed this in a high dimensional space. And we want to do it for different PDEs where we maybe even have like different number of channels. Like maybe one PDE is like only density and it just evolves the density. Maybe another PDE is like electromagnetic fields. So how do we put all of these different like physical systems in the same model? So the trick we use is essentially we have the physics metadata. So this is kind of like describing what is the PDE, like what are the parameters, how many channels, etc. You generate the filters from that. So you kind of generate a bunch of one-by-one convolutional filters. These convolutional filters are used to map the data into your high-dimensional embedding. So for example, like maybe I have, so this is compressible Navier-Stokes. I basically tell that to my like filter assembly step. And it's going to say, okay, it's Navier-Stokes. It has like this Reynolds number, whatever. So these are this is like your embedding kernels. So I have this 4D vector assigned for each of my high dimensional, so I have like 128 dimensional channel dimension is like my latent space, 128. That means I have 128 different convolutional filters that I would need to generate. So I take like one of these and I kind of convolve it all around here. That gives me a kind of latent field. So it's basically like a linear combination of density, pressure, velocity, right? Like it's a linear combination of these at each position in time. So this is a way of taking like an arbitrary PDE, embedding it in the same space, right? And then, so once you do this, you essentially want to solve for a good filter for each type of physics, which is like pretty easy because it's only like 4 times 128. Like it's really small. You want to find a good filter for each type of physics. And then you want to basically find a universal PDE solver. So like once you've embedded all of these different physics into this high dimensional space, you want to find a kind of universal model that works for all those types of physics. And that is kind of like the foundation model. So the model we use, so this paper was led by Mike McCabe, who's a grad student at Colorado, and he's staying with us for a year. So once you've kind of like embedded it into this model, it's a transformer. So it's kind of related to this thing called a Swin transformer. It's like a vision transformer, but it is like separate self-attention steps. So you have this time self-attention. So it kind of looks back in time and does a attention step. Then it looks in space. So it looks like, okay, like linear combination space in X dimension, Y dimension. And then it goes through like an MLP. And so you repeat this block many, many times. It's basically like a transformer specifically built for like 2D PDs. Okay. Once you go through this, so that's kind of like this universal PDE solver. in 128 dimensions. Then you decode it, you do this field reconstruction. It's basically like the inverse of this, and you get your predictions out. So that's the basic idea. So it's a single transformer model that can deal with any, I guess, any type of like physical PDE. I mean, like we've only tried it on, I think, forward PDEs, but it's like the principle is that you could maybe apply it to many different PDEs. Okay, so this is like the ground truth in the bottom, predictions at the top. I mean, like a lot of people show these, like it's hard to tell from just looking at these, but it looks good, right? The really interesting part is when you compare it with like specialist models. So the blue, orange, green, and red, so the first 4 columns in each batch, those are the specialist models. So those are trained just on this specific PDE. The 4 columns to the right here, those are the multiple physics pre-trained models. So those models, you show them all the types of PDEs except this specific task, and then you fine tune on that task. Now, all of these, so all the PDEs we trained on, they are like separate physical systems. And often, so we trained on incompressible Navier-Stokes and compressible Navier-Stokes. Those have different number of variables, right? Like compressible has density, but incompressible just has velocity. So you're kind of like, you're trying to teach this model general concepts, but with like different variables. So it is cool that it kind of transfers to other PDEs that it was trained on. So this is like initial, I guess, observations that you do get like physics transferring between PDEs, which I think is really cool. So yeah, so this is from the multiple physics pre-training paper. You get really nice performance, even for like tiny models. You do get like really nice performance, even against much larger models. It's just by like pre-training it on many different PDEs, you get, and I don't even think it's like architecture dependent. It's kind of like you pre-train this model, many different systems, it will usually help you. So one other thing that you need to keep in mind, if you are doing kind of like multiple physics pre-training, this is more of like a technical point, but in physical systems, some systems are much more expensive to simulate than others. So if I look here and each of these arrows is like a different type of physics, what can happen is in a single batch, maybe I am like simulating this system, and you see there's all this wasted time here, and it kind of like accumulates. So if you're doing multiple physics pre-training, essentially you want to have gradient accumulation as long as possible so that you, on average, have fewer missed cycles. So it's just a little trick that you wouldn't really have in language or vision, but you do have in multiple physics because you're dealing with like PDEs with different numbers of fields, maybe different resolutions, and so on. So just something to keep in mind. Yeah, so this is the result of video MAE. So it's like you take a like video transformer model, you show it like YouTube videos, and it does improve. So like this green model is from scratch. So it's like uninitialized. This video MAE is pre-trained on YouTube videos. So it does help you. Like even showing cat videos does help you, even though it sounds ridiculous. It's like maybe cats are kind of like fluid-like, I don't know. But you see, like if you do train on physics, like it does help you. So if you train on multiple physics, it does help you. So that's the takeaway. So the last direction, so I talked about like this way, I talked about this way. So we also have some projects that are kind of like in the middle. So like taking some things from language, some things from traditional models, combining them. So this is a paper called AstroClip. It's led by Francois Lanous. This paper is essentially finding cross-modal embeddings for images in spectra. So if I have an image of a galaxy and I have the spectra of the galaxy, I can maybe encode both of those to the same dimensionality space. And instead of like trying to predict the spectra from the galaxy or trying to predict the galaxy from the spectra, what instead I could do is just look at the latent vectors themselves and kind of like bring them closer together. So I make the embeddings for galaxy images close to their spectra embeddings. And the other thing I do is I push apart unrelated spectra and images. Okay, so this is called contrastive learning. It's what's used in, I think in like stable diffusion models, you're trying to embed text into the same space as like image representations. And you're kind of like pulling them closer together, pushing unrelated things farther apart in this abstract vector space. Once you have this, once you have this, you can do other tasks with it. So you kind of get this like free downstream tasks. So for example, like if I have this image and I map it to my vector space, what I can do is like a nearest neighbor search in that space. And I can find, maybe I have like a catalog of spectra. I can find like a matching spectra for that galaxy in this high dimensional space. And then I can infer like physical things from that spectra. So I say like this spectra is maybe like a good match for this galaxy. So this spectra has this redshift, this mass, this stellar mass. So it's basically like zero-shot prediction. Like I did not train explicitly for redshift prediction. I only trained to put images, like galaxy images and spectra in the same space. And now I get these tasks for free, kind of. So it's cool because like if you actually apply this, so this is an image that wasn't in the training set. The red is its true spectra. And you can see like it kind of pulls out spectra that are actually like pretty reasonable. Like these spectra kind of look like it's true spectra, even though it wasn't trained to predict spectra. It was only trained to compare spectra and images. And this is another one. So I think these are pretty cool. So it's like a cross-modal embedding for astronomical data, which is cool. And so, yeah, so this is like, okay, if you want to do like photometric redshifts with like the whole image, you could do that with this because you embed the image into this latent space and then embed the redshift and you kind of like, you look at oh, this is like a similar redshift. So obviously like spectra like gives you the redshift, but it's cool you can get those from image. Now, this obviously is not close to state of the art for photometric redshifts, but the really cool thing is like it was not trained for redshift prediction, right? Like this redshift prediction is basically like free, which I think is cool. Okay, so that is the end. So in summary, I presented this new research collaboration called Polymathic AI. We're trying to build foundation models for science. So pre-training large models on tons of scientific data. And so that you as a scientist can kind of take one of these models, specialize it for a task. We have initial results in of like, what happens if you train on multiple physics? What happens like if you make language models better? And then how does cross-modal embedding kind of work for science? Yeah, so thanks again for inviting me, and I'm happy to take questions.
Great, thanks very much, Miles. This has been really interesting. Okay, so I think Arif, you had your hand up first.
Yeah, I also posted my question on the chat. I was wondering how you kind of determine the scale in which like you include certain PDEs, for example, to train your model on. Is there kind of, like walk me through what informs you in like deciding what kind of data to feed into your model?
Yeah, that's a good question. So I think like generally, I don't know. Like if you're asking like how do you pick related PDs, I don't know. I think like that is an open research question. I mean, it's even an open question in like well-studied foundation models. Like we still don't know what the best ratios of like text data are in a data set. So it might be hard to answer this, but so in our data set, we basically just trained it on this benchmark data set called PD bench. It's basically just like 4 PDs with lots of data. So we just chose it because it was there. I think in general, like it depends what you're testing, because like this is still at the experimental stage. We're kind of seeing like how close are PDEs before they start improving performance. But I think it would be interesting to try like further away and further away PDEs. Like maybe you start looking at like quantum stuff and see like how that interacts with the predictions and whether there's any like domain transfer. I guess like, okay, so scales, you also mentioned scales. Like, so we do this normalization scheme here. I forget what that stands for, but it's like this kind of normalization used in vision transformers. And so basically no matter the scale of your PD, it's all kind of like normalized. And then, so that makes the embedding a bit easier. And of course, like in the transformer block, you have a lot of layer norms. So that's going to take care of some of the normalization. Yeah, I don't know if I answered your question.
Yeah, you did. I'll give it some more thought, but thank you.
Yeah.
Melissa?
Whoop, sorry, found the unmute button. I guess I have a related question. So at the beginning of the presentation, it seemed your scope is really trying to collect data from very diverse fields to create these foundation models. And you mentioned that computing resources are one of the challenges, but I would imagine that actually collecting these data sets and inputting them in and like embedding them in some way that is understandable by one machine learning model is an absolutely gargantuan task. Could you comment on that, or any ideas you have?
I mean, I completely 100% agree. Like that is like the compute resources I mentioned, that is like, that's kind of the more physical constraint on a lot of academics. But there is like the time constraint. You obviously can't collect every single data set in science. I think like part of it is that, so part of the multiple physics pre-training result is that you don't really need to have your pre-training data that close to your fine-tuning data set. Like you could have cat videos and then fine-tune on compressible Navier-Stokes. And it's like, you do still improve. So I think the major difference between large language models and foundation models for science is that with foundation models for science, I think you would usually expect to fine-tune your model. Like, I think there's just the space of possible scientific data sets is like too large to expect there to be like a single universal model that knows like all of your weird like PSF patterns and like it knows like everything. Like, I think that is unrealistic. So I think the fine-tuning part is going to be really important for scientific foundation models. And that also means it's not as big of an issue if you can't collect like every single field of data. But yeah, that is something like we're spending a lot of time in, is the data curation aspect and like slowly accumulating more and more data sets and thinking about, okay, like what is the best universal architecture? I mean, there are some ways of making language models understand images. So there are ways of embedding totally different modes of data into the same space. So it's not unprecedented. And I think it's just like, yeah, I think like, yeah, I mean, I don't really know the complete story here, but I think, yeah, I mean, the data curation is definitely a big aspect of this. Yeah.
Yeah, thanks. That's very interesting.
Ashish?
Hi, nice talk. So you mentioned earlier about biases, and you also mentioned about how numbers are not, LLMs are not good at numbers, you have XVAL, etc. So in general, what do you think could be the basic hallucination effects that you may start seeing initially? And what would be ways to go around that?
The hallucinations of...
From your science foundation model when it's done.
Oh, I mean, it depends like which way we go. So actually, the only generative model in our 3 papers is the language model. The multiple physics pre-training model, it's not generative. Like it's a one-step prediction. So it's, I think it's like a bit safer against hallucination, where it's like of course you can make mistakes, definitely, but it's like it's not really like hallucinating things. And then the astroclip, of course, like all of like machine learning, of course, can make like tons of mistakes. Yeah, I think that one also maybe doesn't, like, you don't have to worry about the hallucination as much because you're kind of like anchoring it in real data. So like if you embed a galaxy, you do nearest neighbor against like a real spectra, for example. So that part's kind of like maybe a defense against the hallucination problem. But yeah, the language model, I think that could totally hallucinate. And I haven't really thought about if it's going to be different from normal like deep learning errors, because like deep learning makes a lot of errors. I don't know if the generative aspect is going to like change the type of errors you see. I don't really know. I haven't really thought about it, but it's a really interesting question.
Thanks. Okay, and we'll take one final question from Zhang Yang.
Hi, this is Xiang Yang from Berkeley Lab. I have a question, maybe a comment also. So there is a fundamental difference between natural language and a scientific domain, which is that the scientific domain often deal with continuous multi-dimensional phase space rather than tokenized vocabularies, right? And that makes some of the applications, they have to do data pre-processing and to fit that kind of paradigm. And it's motivated to do so because that paradigm seems to scale very well. And I'm wondering, what's your vision of dealing with this multi-dimensional continuous space in scientific field? Like, do you suggest like tokenize that field into an image-like style or something else?
Yeah, so I don't know. Like I don't know the best answer here. I guess like there are some multimodal approaches, because industry, like if you talk to the new ChatGPT, like you can just dump images in and it can kind of like describe them. So there are, of course, like ways to mix these modalities. And of course, like that is two-dimensional data with a one-dimensional sequence. So it's kind of like mixing dimensionalities a bit. So like maybe you could take that route and just like keep kind of like adding more tokens to deal with the dimensionality. I kind of think like maybe that's not the best way, because you're kind of relying on the language model using positional encodings to kind of like figure out like when the simulation wraps around in the second dimension or something. So yeah, I don't really know. I guess I think like there's also the question, is a universal foundation for model for science, is it actually just going to be one, or are you going to have like multiple? Like maybe you have like a 2D foundation model for science, a 3D one, and like maybe a graph one. So I also don't know if the final models we release, which might be like model or models, I don't know. I don't know if that is going to be like a single universal one, or like maybe subcategories to deal with different dimensionalities. Like from what we've seen from language, the more kind of data you put in, even if it's completely unrelated, it kind of helps the model learn. So I hope that we can have like 3D data and 2D data and sequence data all in the same embedding space. Like I think that would be the optimal outcome, but it might, yeah, I don't know. I don't know what the answer is going to be. But yeah, this is a great question. Yeah.
Yeah, thanks for the answers. Some of them are very inspiring, actually.
Thanks.
Good. Okay, we're past the hour, so thank you again very much, Miles. This has been a very interesting, and I think there'll be many discussions in our own institute as we digest what we're saying.
Okay, thanks a lot.
Everyone look out for an announcement about next month's seminar soon. Otherwise, happy Thanksgiving, everyone. Thanks.
Thank you. Bye.